All right, so let's get started. Just to repeat that I'm Nick Knight from SiFive, and this talk is on behalf of Hong Rong, who did the work. So this slide is summarizing the OpenXLA project. SiFive is one of the member companies. We are a RISC V processor company. We design RISC V processors. These are standard RISC V processors, except we have vector instructions and matrix instructions. You can tile these things in multi-cores and scale them out in usual ways. And a couple of years back, we selected IREE as our AI compiler of choice. And we've been collaborating with, actually, you probably need the microphone to get people online. I'll stop wandering. We have selected a few years back to work with the IREE team. And so our AI software stack is based on OpenXLA with IREE as its compiler. And I think that's all I need to say about this slide here. So it works. We have we've had a success story with this software stack. We're a very small company. We have about 10 people doing AI things, hardware and software, and so we can't really staff a huge team to do this. And this OpenXLA and IREE gives us a great solution. Here we have was this BERT large or something? It's another language model. But anyway, we are able to bring up real-world neural networks and real examples with them on our cores with a pretty small effort. So this was just a demo we gave at a conference recently, doing some kind of a natural language processing stuff. So it's a thank you for the software. It's a great tool, and it's really enabled us to be a lot more productive. Just to give a talk about where we're going next and where our active work is. So we have our FPGA for one of our cores actually hooked up on IREE's dashboard, so you can see the performance online. Thanks to the IREE team for helping us get this integrated here. So yeah, our stuff's in regressions, and the results I wanted to share today was some of the more recent work is integrating our microkernels into IREE. So the compiler folks have been saying since the 1960s that they're going to put people like me out of work. But the reality is that the inner loops are, you still need us performance programmers to write those inner loops, especially on this processor, which is an in-order processor. It actually requires some careful hand scheduling, software pipeline of the inner assembly loops. And so that's what we do well. And so the microkernel approach is a great way to take that assembly code that we work pretty closely with the compiler team, but they can't quite get that. They'll get to 90%, but we can do 100% with a handwritten assembly. And so the microkernel integration, this is just a standard approach in performance libraries, especially in linear algebra libraries. Take Bliss for an example, to use microkernels. So we have integrated this is showing, let's see, softmax on this one here. I think we had some other results on a previous slide deck. Maybe that was from the last summit, talking about the quantized matrix multiplication. So this one here is showing improvement in softmax versus the compiler code gen here. And integrating the microkernel makes it run faster. I think that's the takeaway of this slide. Now, my role in this project was mainly working on the exponential function used inside the softmax. And that's very specialized for the RISC V vector extension. Did a lot of Remus algorithm to find the coefficients, and a lot of like low-level tinkering to get a good exponential function, because the way you normalize the translation invariance, you can basically run an exponential function that's only on the negative reals. So you basically don't need to handle the positive reals. You can shape some instructions right there on your exponential. And there's lots of little tricks you can play. And then because in softmax, one of the terms is 1, so you're adding a bunch of numbers with 1. So you can basically flush a lot of subnormals or smaller numbers because they're getting added to 1 anyway. So we can debate that by the coffee machine if you want. But so there's a lot of little tricks we can play, and I don't necessarily expect the compiler exponential, which is probably a more general thing, to get all those tricks. So that's the type of tricks we can play with a microkernel, and all this is very specific to our hardware. We're currently working on some hardware acceleration for exponential functions. I think the team owes me an arch spec today, so please see it soon. And so that will plug in here. via, see if we have a slide on that here. Maybe the next slide. So this was summary of the microkernel integration. So this allows us to vectorize and code-gen RISC V vectors. Many things the compiler does really well, like memcopy. Compiler can beat me at memcopy usually, just because I'm too lazy to do like dynamic realignment and stuff like that. But stuff that requires tiling, I tend to be able to beat the compiler, at least on our in-order cores, because the compiler is not going to try every possible tile size. And I'm actually willing to. I'll spend 6 hours or 8 hours in the office, run a million, generate a million assembly codes, benchmark them all, and take the best one. And most people are not willing to type clang and wait 8 hours for the result. So, so that's why microkernels are great. Yes, the last bullet point's interesting. The microkernel can be a reference for the compiler to get better code gen. This is a more general role of our team as we work closely with the compiler team to share insights and say, inform the scheduler model and be like, hey, actually, if you tweak these latencies or occupancies a little bit, maybe it'll. So it is important to do the performance programming work, not just to get the results in IREE or in the application, but also to improve the compiler for other applications. And some of the knowledge we've gained on these microkernel development has improved our spec scores and things like that, which some people care about. So it's also, there's a feedback loop between the library design and the compiler design. So this picture is showing the way we can apply the software stack to our to a CPU and a deep learning accelerator. SiFive has a couple different ways of connecting accelerators to our hardware. I actually distinguish accelerators and coprocessors. This one's showing an accelerator. Or actually, no, sorry, it's showing a coprocessor, VCIX, as the vector coprocessor interface, which they call V6, which I think is kind of clever. And so this is the sort of the general model of how we, for a single, or maybe that's a 2-core machine, how we would, map OpenXLA to this hardware. It's just a cartoon. Okay, and then the other point here is one of the other things we're working on, SiFive. We pretty frequently get requests from customers like, hey, we're trying to build this cell phone and we have this raw data coming in this weird bespoke, fixed point format, and we want to convert it to RGB. Can you add a new vector instruction to the RISC V ISA for this really specialized task? We say no, that's bloating everyone's code for this one specialized thing. This comes up all the time with customers. And so what we have done is we have added surprise custom instructions. So this is for the case of vector instructions. We also can do custom scalar instructions. And so customers can design. It essentially looks like another vector functional unit that gets plugged into our pipeline. We have assembly opcodes that are kind of templates for this and intrinsics and whatnot. And so what Hongrong has been doing is piping that through the IREE stack so that you have an MLIR dialect that can basically peephole things that are that can map to the custom instructions. So the typical problem we have when customers use this vector coprocessor interface is like, hey, we built this new instruction. How do we get the library support with it? Someone's got to go write all that software. And this is the power of the MLIR dialect that Hongrong is working on, is it will actually enable the customer to get an optimized AI solution using whatever their new instruction is. So maybe they have a better exponential than I do. They can swap it out, add the hardware for it, and basically get a whole AI software stack on top of it and not have to do too much work. So this is work in progress. I don't know if this has been PR'd upstream yet, but this is one of the other things we see as a power of the MLIR approach. Was there a question in the back?
Yeah, but maybe I'll ask it.
Okay, I think I'm probably almost done. There we go. Thanks for your attention. Time for some questions. Yes.
Thank you. So I'll preface this with, I don't know much about hardware, so this may be a stupid question, but for these custom instructions, is it difficult to know to preload memory into the cache? Is there a cache and that you load from, and you still have like RAM that's like slow to load from, and you are constantly like CPU is constantly guessing to load certain chunks of memory and stuff like that? And for these custom instructions, I'm assuming you don't have that much knowledge over what it's going to do. So is it harder to load into cache, and therefore is there a cost to having these custom instructions?
Yeah, I think you do know a lot about hardware. Good, very good question. Yes, so the first comment is that our custom instructions are actually only arithmetic instructions. One of our customers, who I don't know if it was publicly announced, who may or may not be in the room with us today, has used this actually to implement memory operations, but that actually added a lot of burden on them because then they had to implement all kind of memory coherent stuff behind the scenes to get to work. So actually the way we intended for these custom instructions is really just to be another vector arithmetic unit, like maybe a matrix multiply or something like that. In that case, the memory issues, but there are interesting issues with, because it can allow a variable instruction latency. So you might build a big beefy outer product or something, and it might take 100 cycles, or maybe it varies based data dependent latency. How does that hook in with the rest of the pipeline? And we just have kind of a standard scoreboarding approach. It can read and write to the vector register file. So it just sort of scoreboards with like the way any other vector instruction would work. And that's a way of supporting variable instruction latencies. So it's, but it's very tightly coupled. It uses the vector coprocessor interface, uses the RISC V vector register file to source operands. You can build like an SRAM inside the coprocessor if you want, like the outer product accumulator, but it really works by reading, loading, and storing data to and from the vector register file. And then you use the standard RISC V vector loads and stores to bring the data in and out. That's sort of like the standard model. Good question.
Thank you.
Other questions? Questions from the internet? Yes.
It sounded like you were saying when people ask you for custom ISA extensions, you say that's nuts, but then it sounds like you actually go ahead and do that. And then you have a software infrastructure that allows Velocity to leverage those quickly. So then do you bifurcate and tree up your ISA, or how do those ISA extensions propagate into future spins?
So in the case of the vector coprocessor interface, the way this works is we have, and I think our patches are upstream LLVM. It basically added assembly, mnemonics. It uses the RISC V vendor, what's it called? The vendor extension space. There's a space of the RISC V opcode space for vendors to add whatever they want. And so it uses that. And so it's a sort of, other people could overwrite that same part of the space. And so you're going to get portability across vendors. V6 is not a RISC V thing, it's a SiFive thing. But we don't actually, the customer implements, we've never seen, I don't think I've ever seen the RTL, the system Verilog that customers have written for this thing. They keep it in-house. We just give them the place to plug it in, like the interface. And so they can use these V6 assembly mnemonics in their code, and upstream LLVM will process them and generate the zeros and ones correctly. But the meaning of those is defined by the customer. So actually, if you took their assembly program and ran it on someone else's hardware that implemented those instructions differently, it would get different results or maybe illegal instruction exceptions. So we don't actually productize our customers' coprocessors. That answer your question? Thanks for the question. Other questions? So I think an interesting area, we've been getting a lot of good discussion on our pull request for the softmax microkernel. Some of the IREE folks have been saying, hey, like, what is the granularity for your softmax microkernel? And I'm pretty sure what we did is we just PR'd this big old thing that does like all 3 passes. And they were thinking maybe just do the exponential part and have the compiler do the rest. But this is the discussion we're going to need to have time and time again about microkernel design, is what is the right granularity to express the microkernel. And PenPon's RFC, she posted last week, or maybe it was this week, about the, for XLA, the microkernels versus subgraph stuff. That's another instance of the same discussion. It's about the granularity you expose for third-party vendors to plug in their stuff. And people like Intel with huge teams and 1DNN and whatnot, they'd be happy just to dump their whole fully connected or conv2D thing with taking a whole thread pool and run it. I'm actually happier to provide like a register tile and have IREE generate the cache tiles and thread blocks and everything, and not touch that part myself. So I think that there are different use cases for different people, and but the microkernel API does need to be, I think, taken seriously and treated at the same level that we're doing all these other RFCs in the OpenXLA mailing list. That's my little manifesto. All right, no more questions. Thanks for your attention, and we can talk more at the coffee break.